Okay, this is IM1. This is lesson 5-4. And we are doing exponential decay. So exponential decay is when the number actually decreases. So it's modeled based on the same function, y equals a times bx, where x is that variable or the exponent. A is our initial amount, and b is our decay factor. In this case, it's actually less than 1, and we find it by subtracting by 1 or from 1. Okay, let's look at a practice problem. So I've turned the page and we're doing problem 3. A kilopascal is a unit of measure for the atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases by about 11.5%. What is the atmospheric pressure at the altitude of 5,000 meters? So we're still going to use this same equation, y equals a times bx. So let's figure out what a is. So a is where we're starting. And what we're actually calculating in this problem is atmospheric pressure. So that means where we need to start. It's not 0, but it's at 101 kilopascals. That's what the pressure is when you're at sea level. All right? So we also are calculating the pressure decrease. So B is the decay rate. So that's going to be 1 minus 11.5 or 0.115, right? Because that's our percentage. So you can either grab your calculator or you can do it in your head. I like to use my calculator to be sure, but the answer there is going to be 0.885. All right, and x is going to be our number of, basically the number of jumps, right? How high we're going. The number of 1,000 meter jumps. So in this case, we are going up to 5,000 meters. So in this case, it's going to be 5. So our equation is going to look like this. Y equals 101, which is our starting number, times 0.885 to the power of 5. All right? And let's put that on our equation. So 101 times 0.885 to the power of 5. All right? And that equals 54. Our significant figures was approximately 3. That was our smallest number. So we'll put 0.8 kilopascals. Right? And that's the pressure at that atmosphere. Let's go down to practice 5. Identify the initial amount A and the decay factor B in this exponential equation. Well, it should look exactly like this. Y equals A times BX. The thing that has X on it should be our decay factor. The thing that doesn't have any variable attached to it or any exponent, that should be our initial amount. Right? So this is going to be our initial. And this number right here is going to be our decay factor. All right? Number 6, the population of the city is 45,000 and decreases by 2% each year. If the trend continues, what will the population be after 15 years? All right, let's do an equation. Y equals A is our initial starting, so that's 45. And then we're going to multiply it. Our factor is 1 minus 0.02 to the power of x. This is 0.98, and our x in this case is going to be 15 years. So 45,000 times 0.98 to the power of 15. I will not expect you to do that in your head. I wonder if I can zoom in better. 45,000 times 0.98 to the power of 15 equals 33235. And we won't try to round it because they are people. All right? And that would be the population. You can check for making sure that is a reasonable answer by saying it decreased and 15 years of decrease. Is that number smaller? Yes, that number is smaller.